Boleh sir.
Okay. We continue our lectures still under the analysis. I think last week we had the first analysis for non-recursive algorithm or iterative algorithm. Okay. I do hope that you understand the concept, the idea, the implementation on how to do the analysis for the non-recursive or iterative algorithm. Okay, as I mentioned earlier, in order to do analysis based on the implementation of algorithm, we have two. The first is analysis for non-recursive, which is iterative, using the normal loop iteration, whether for loop, while loop, or do while loop. Okay, and the second is for the recursive, where we have also the repetition by using the recursive method, where we have the method and the method invoke itself finally become repetition, repeat until the stopping criteria. Okay, so the rest of the, I mean, for the exercise, I think you have to go back to the lab sessions, and for groups 5A and 5B, please refer to the your lecturer, Cik Azizian, especially for the solution for the um, exercise, right? Assignment. Okay, please assignment submit according to the due date. Okay. You don't submit according to that, then basically we reject your assignment. So there's no mark for that. Okay. Please follow that the due date given to you. Okay, around 1 week, based on the session, lab session. For my group, 5C, tomorrow will be a public holiday. There's no lab for tomorrow, but inshallah I will also upload and post that the assignment for today, which is for the recursive algorithm. These two assignment is actually important for you to have the assignment, and you do it based on the this, so that you can understand the analysis part. Okay. For tomorrow, for group 5, tomorrow will be the public holiday. There's no lab session, but after this, I will upload through the Google Classroom the exercise for tomorrow, right? So please read and do it. I mean, do the exercise assignment, and also the instruction. You read the instructions and also the due date. Okay. Um, okay, we continue our lectures. There is someone still requesting to join in the class. So please use your um, Google, your Google Mail, Google email, your ITM emails. Then you can join the class automatically. If outside from the your ITM, especially when you are using different email, especially for personal email, then I do want to accept that the the, the request. Okay. Okay. Now we move on to the recursive algorithm. Okay. We have done the non-recursive, which is the iterative, and for today we continue for the recursive algorithm. But in terms of analysis, in general, basically a bit different. Even though some of the concept basically the same, maybe when we use again the summation, the log, and so on and so forth from the mathematical perspective. But in order to do receive, due to the analysis for receive, basically different from the what we did in general for the non-recursive algorithm. Okay, that's why you need to have this topic so that we can discuss, and I will guide you how to do the analysis for the recursive algorithm. Okay, before we do that, you need to understand the basic recursive. What is the recursive? Or it may be called recursion. recursion is actually for the mathematics topic, and from us we have the recursive, which is a recursive method or recursive algorithm. Okay, so in general, is a general solution, which is where we break the problems into smaller version of itself. We have the problem, bigger problem, break into a smaller version of itself, become smaller, 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 until certain point. When we reach that point, so we have to stop for the iteration. Become the iteration, repeat, repeat, repeat. The repetitions occur many times until certain criteria will stop. That is the repetition based on the recursive. Okay. In general case in the recursive domain in which a smaller version of itself is called. Mean we have the recursive method, and invoke itself mean it call itself, and finally become smaller, and after that it stop. When we call that the method, it become repeat until the repetition stop with certain condition. Okay, so must eventually be reduced to a base case. That's why we have the base case. The base case is the criteria, the stopping criteria. We stop until the base case, because the base case basically is a simple problem that we can solve directly. So with n equal to 1, for example, if we reach to that, then we will solve. N equal to 1, automatically we take that the result for the n equal to 1, automatically 1, for example. Okay. So logically, you can think of a recursive method having unlimited copies of itself. This is how we can imagine that for the recursive, basically, uh, let's say you have means you have a problem, you have the method, and after that it become repeats, and for each repeat it will copy basically the same thing, but it's a smaller version. So unlimited copy access, and calling it own code, set of parameters and set of local variable. So we have a set of bigger problem, a method with variables, parameters, and also the code, and after that you will copy again, become smaller with the same copy with codes, parameters, and set of variable, and repeat again until certain point we stop. Okay, that is the overall recursive when we try to understand in general what is the recursive algorithm. Okay, this recursive algorithm, the general algorithm, if the problem can be solved for n, solve it. Okay, this is actually the first step. If the problem can be solved for n, mean we have a very simple problem, small, then we can solve it directly, then solve it. Else, if the problem cannot be solved directly, so we need to do what we recursively apply the algorithm to one or more problem involving smaller values of n. Make problem bigger, break into the smaller, become smaller, smaller, until we reach to the certain problem that we can solve it directly. And that's solve it. And after we finish that, combine the solution to the smaller problem to get the solution to the original. This is the actually in the implementation behind the source code, when we apply the recursive behind it, basically it will apply data structure, which is a step. So when we solve it, we push to the step, push, and after that, pop in order to combine back the solution, and finally we can solve the solution to the original, which is actually the original solution, the end just now. Okay. Okay. Recursive step. Look at this. For example, consider the following list of numbers. Let's say we have the list 24, 88, 40, 37. This is the list or the array. A list can be defined recursively. That's it. We have the what we call that, the language, the formal language. You will learn about the formal language. We have this a list. The rules is a list is a number, or a number, comma, list. So we can break into three components: the number, the comma, and the list. And finally, we can establish the rule: list is a number, and followed by number and the list. This how basically it become the recursive number, list, number, list, number, where we can break down the problem into smaller. Like this. Let's say we have a 24, 80, 88, 40, and 37 just now. So the list based on the rules, number, comma, and list, we have number 24, comma, followed by the rest of the list, 88. The remaining is 88, 40, and 37. And when we break down to become smaller, where we have the list just now, the remaining three element the list, 88, 40, 37, and put that the rules, the next rules, where we have the number 88, comma, 40, the remaining, and 37. Okay. And finally, we have 40, comma, 37. And finally, we have only single element for that 37, where actually that is the stopping criteria. Then we stop from the recursive, from the repetition, because we have reached to the terminal of the problem. Okay. This is how we can see that the overall idea of recursive thinking of the idea of recursive step. Okay. And this is the example, good example, in order to understand the recursive step. Consider the problem of computing the sum of all the number between 1 and m. Okay, 1 and m here. So let's say n equals 5. Can you see that this whiteboard clearly?
Yes.
Okay. Let's say n equal to 5. So we need to get the sum if n equal to 5 like this, where we have 1 plus 2 plus 3 plus 4 plus 5. This is the sum of n equal to 5. So what is the answer here? Is 15. The answer will be 15. This sum of n equal to 5. Okay, in the recursive, basically, we have that the formula here, we have n plus is a function n minus 1 here. Okay, in the recursive perspective, where we have the if sum of n, if n equal to 1, when we try to sum 1, so is equal to 1, correct? Because sum of 1, 1. If sum n equal to 2, 1 plus 2. If sum equal to, for n plus n equal to 3, 1 plus 2 plus 3. Okay, so the base criteria will be n equal to 1. N return 1 automatically, because this is the base criteria, the stopping criteria here. So when we do this, basically we have the n. These are our formula is n plus function n minus 1. This is a recursion n minus 1. So this we can see here. Let's say n equal to 5 just now. So we have 5 plus this function n minus 1. 5 minus 1 become 4. Correct? Is it correct?
Correct.
Okay.
Yes, sir.
Yes.
Now we have to reduce it here. And now become 4 plus 4 minus 1, 3, correct? And this 3 plus 3 minus
Yes.
1, 2, right? And 2 plus 2 minus 1, 1. And after that is 2 minus 1 is 1 here. So we have 1 return 1, correct? Because n equal to 1, 1.
Right.
1, right? So this return 1, right? Because this function, when function will execute this, it will return. So the return value is 1. 2 plus 1, 3, correct? Then this become 3. And 3 plus 3, 4. Okay?
5. 3, 5.
3 plus 6, sorry. 3 plus 3, this return 3. 3 plus 3, 6. We return to this function. This is a small copy of the bigger problem becomes smaller until this. You copy the same thing, right? The parameters, n minus 1, the code, and so on and so forth. So 6 plus 4, 10, right? 10 plus 5. So we got the answer just now, 15 here. This is how the repetition. Can you see that the repetition here? This will
Yes.
reduce until stopping criteria. What is the stopping criteria? When n equal to 1. This stopping, we stop the repetition. After you stop, you will return the values. The is 1 here, return 1 because n equal to 1. And 2 plus 1, then combine back as look at the back to the slide here. Sum of 1 minus n is n plus f n minus 1. So regression part is n minus 1 here. And the combination here, we need to combine here. This is a combination. And finally, 1 plus 2, 3. Then you will return to this. And 3 plus 3, 6. We return to this because this is a function. 6 plus 4, 10. 10 plus 5, and finally you get the result, 15. This is how the repetition. Clear? This is a recursive.
Sir,
Yeah.
sorry. N plus F bracket N minus 1 tu dapat dari mana?
Oh, itu formula matematik lah.
Oh, dia memang formula tetap lah.
Dapat tu panjang cerita lah. Nak cerita kan. This is mathematical formula. When we have this like 1 plus 2, we can recursion it basically n plus fn. So the next is we have n. After this, we have n times f n minus 1. This formula for what? Just now plus. So formula for this. Jadi apa ni? So jadi factorial, right? Jadi factorial. So this is summation, but the factorial basically the same thing. Here. Okay, the next slide. Look at the next slide. Okay, this is the implementation from the programming perspective, where we have some integers here. Okay, these are programming from here. These are the theory just now from the perspective mathematics. From the programming, we have some integers and the parameters here, which is n, right? And if n equal to 1, then return 1, because this is a base criteria. Let's say if we pass the value of 1, automatically return 1, because the sum of 1, 1. Loading as is, so we put that there just now, n plus the function here, some integer, and n minus 1. Correct. So these are the function, the same function. So we call back here. So when we have that, let's say just now we have n equal to 5, this becomes 5, right? And this is n not equal to 1, no, false, it go to s. S, now we have 5 plus some integer here, 5 minus 1, we pass 4 here. And hold that the result first. And finally, this become some integer 4, and this 4, because this n equal to 4, some integer here is 3, and this 3 plus some 2, and after that 2 plus 1 here. This is the same thing, right? You look at this on the left here. This is what we trace just now from the mathematical perspective recursion. This is what we trace here from the perspective of programming, right? This will be n minus 1. If call back, become repeat until stop here. Stop here, because the base criteria. Okay? So this become in one basically we return 1 here. Because we stop here 1, return 1. And 2 plus 1 pass to this 3. After that 3 plus 3 6. 6 plus 4 10. 10 plus 15. And finally, when we run this automatically, we can get the answer 15. Correct?
Yes.
Correct? Understand?
Yes.
Okay.
Yes.
Any question so far for this? No question.
No
No,
question.
no, sir.
Okay. So this diagram basically the same thing what I wrote just now. The same thing. So main some integer 5 reduce 4 3 2 1. 1 will stop because the base color. Then the result 1 plus 1 and after return 2 plus 1 and 2 plus 1 return 3 until the that return 3 6 10 and 10 plus 5 15. So the same thing. Okay, clear? Okay, now you go to factorial. We go to factorial. Basically the same thing. The factorial the same thing, but we change only the here the from plus to multiply. Okay, and the stopping criteria. What is the stopping criteria? Look at that question to the side. M factorial. If n equal to 0, return 1. So here is we change to 0 because the factorial 0 is 1. So the stopping criteria is 0. Just now 1. It depends on the problem. So factorial 0 is 1. So basically we can have this 1 time here is 0. Correct? 0 until this. So the 0 return 1. 1 times 1, 1. Okay, now got 1. 2 times 1, 2. And here 2. 3 times 2, 6. Okay, 6 times 4, 20. 20 times 5, is it correct?
6 times 4,
24,
24.
sir.
24. Okay, 24 times 5, 100. 120. So 120. So this equivalent to, if we have just now 5 factorial equal to 5 times 4 times 3 times 2 times 1. Correct? So 5 times 4, 20. 20 times 3, 60 times 2, 120. The same thing. Okay? Clear? This similar to just now. You just change this, multiply. And the combination is until not 1 because here become 0, right? This is the difference. A bit different with the summation just now because it stop is until 0. Mean 1 plus 1, 0. N 1 minus 1. So this become minus 1, minus 1, minus 1, minus 1. You can notice that this actually is n minus 1, right? This n minus 1. So this 5 minus 1, 4. This n minus 1. This become n minus 2, n minus 3, n minus 4. Here n minus n. Correct? Is it correct? Is it correct? Because n 5, right? 5 minus 1, 5 minus 2, 5 minus 3, 5 minus 4, 5 minus 5. And stop 0 here. But from the recursion perspective, we use that actually m minus 1 because m minus 1, m minus 1, the remaining m minus 1, m minus 1. That is the form of the recursion. But from the other perspective, it look like this. M minus 1, M minus 2 for each iteration. M minus 3, M minus 4, N minus N. Because the stopping is 0. For summation just now, M minus N equal to 1. Because the stopping is 1. Clear? The base criteria. Clear? Any question? Ada soalan? Tak ada?
Ada, sir.
Okay. Look at this implementation, the same, but the condition is n equal to 0. Just now n equal to 1. Return 1. Else n time factorial n minus 1. So it become repetition. Repeat until n equal to 0, it will stop. That is the repetition. As we compare to other repetition by using normal loop, for loop, while loop, and do while loop. Okay, clear? And also, factorial can be implemented by using non-recursive or normal iteration, the factorial. Like this, integer, let's say we give some variable, fact value equal to 1 because that the minimum is 1. We will return 1. So give the value 1 initialize. So when n greater or equal to 1, whatever n greater or equal to 1, then we will execute this. When this true, fact value time equal to n, mean fact value equal to fact value time m. And after that, we have to reduce one by one, m minus 1, and return fact value. When we execute this, basically we get the same answer, which is 150, but different in term implementation. The first one was using the recursive technique. The second here, the example factorial implementation, using the non-recursive. Can you see the difference? But we can solve the same problem. The implementation. Can you see the difference? Clear?
Yes.
Okay. This is actually the same thing what I already explained just now. And we go to the third example. The third example, I think. Just the third, based on the first is summation. The second one is factorial. The third is Fibonacci. Do you know what is a Fibonacci? What is a Fibonacci sequence? In mathematics, we have this Fibonacci sequence. What is Fibonacci sequence? So let's say we have the n here, n equal to 0, 1, 2, 3, 4, 5, 6, until whatever n here. The Fibonacci sequence here is, we have the Fibonacci of n here equal to, if n equal to 0, this is the base criteria 0, if n equal 1, 1. This is the base criteria, two base criteria. Just now for the factorial summation, we have only one base criteria. Depend. Sometimes when we want to do two, depend on the problem. But Fibonacci, we have two base criteria. If Fibonacci n equal to 0, 0 is 0. If Fibonacci 1, 1. If Fibonacci n equal to become 0 plus 1, 1. 1 plus 1, 2. 1 plus 2, 3. 2 plus 3, 5. 5 plus 3, 8. And so on and so forth. Okay? You see this, the pattern? This is called the Fibonacci sequence. Clear?
Yeah.
Okay, look at the formula. So the formula can be, in order to get that this become okay, if n equal to 0, okay, if n equal to 0, you return 0, right? If n equal to 1, return 1. Okay? If n greater than or equal to 2, so we return what? How to write this formula, Fibonacci here? We have a Fibonacci n. So, this is a pattern, right? This Fibonacci 0, Fibonacci 1. Okay? And so, this n, so become, the formula is Fibonacci n minus 1 plus Fibonacci n minus 2. That is the formula. So we can write Fibonacci n minus 2. Okay, let's say we take this 2 here. N equal to 2. So this 2 minus 1 and 2 minus 2. Because n greater than or equal to 2, right? N must be greater than equal to, we apply this condition. If n 0, this is the automatically the return value. N equal, this is automatically the return value. If n greater than equal to 2, then we have to take this condition, right? So 2, now 2 minus 1, 1. So Fibonacci 1, 1.
1.
Correct? So the return is, this are return equal to 1, right? Okay, Fibonacci n minus 1, 0. What is the 0? The return also 0. So 1 plus 0, 1.
1.
Correct? Okay, another example. If n equal to 3, so now 3, this 3. Okay, 3 minus 1, 2, right? 3 minus 2, 1. So Fibonacci 2, what is the Fibonacci just now? We got 1. Correct? 1, we got 1. 1 plus 1, 2. This is the answer, correct? And so on and so forth. That is the recursion. Clear?
Yeah.
Okay. This can be written like this. Okay. Based on this formula, basically can be simplified like this. The formula we have Fibonacci 0 equal to 0, Fibonacci 1 equal to 1. If Fibonacci 2, so we have Fibonacci what? Fibonacci what?
1
1 plus
plus F0.
0. If Fibonacci 3, so we got Fibonacci 2
2.
plus
1.
1. If 4, then 3 plus
2.
F2. And so on until just now, Fibonacci n equal to n minus 1 plus n minus 2. This is how we can get back to the formula just now. N minus 1, n minus 2. Clear?
Yeah.
And if you notice, this is a recursion. Okay? This is a recursion. And this is also a recursion. Recursive. This is also from here. And finally, this is a recursive. Okay? Or you may look at from this graph. From this graph. Okay. Let's say we take this 5. Take a simple 5. Fibonacci 5. Fibonacci 5, based on the function just now, we have Fibonacci n minus 1 plus Fibonacci n minus 2. When you substitute the value n minus 1, we take example n equal to 5. What is the answer? So based on the graph here, this we can see clearly the recursive basically. So n minus 1 is 4, correct? Plus 5 minus 2, 3. Is it correct? Okay, now the next is we take this Fibonacci 4 minus 4 minus 1, 3. 4 minus 2, 2. Correct?
Right.
Okay, here we need to derive again. 3 minus 1, 2 plus 3 minus 2, 1. So the stopping here, we reach the stopping, right? We stop here for this. But here we need to derive again. 2 minus 1, 1, stop. Plus 2 minus 2, 0, stop. This is a terminal. And here we need to decrease 2 minus 1, 1. 2 minus 2, 0. Then we stop. Stop. But here we need to derive 3 minus 1, 2 plus 3 minus 2, 1. Stop. And here 2 minus 1, 1 plus 2 minus 2, 0. And we stop here. Okay, now we trace. Okay, 5 minus 0, what is the value? Return
0.
0. 1, return 1.
1.
1 plus 0, 1. Here. Penalty 1 is 1. 1 plus 1, 2 here. Okay. Here, 1 plus 0, 1. Now, 2 plus 1, 3. Correct? 3. And here, 1 return 1, 0 return 0. 1 plus 0 is 1. And 1 is 1. 1 plus 1, 2. So, 3 plus 2 equal to 5. Then we obtain this. Can you see this? The different from different perspectives. But this when we trace like the graph here, this is actually the recursive. You can see that the repetition. We divide and with these are the bigger copies, smaller copies, right? These smaller copies until we stop here. That is the meaning of divide into a smaller copies unlimited itself. As we uh, discussed just now, which is we go back to this here. You can think of a recursive method having unlimited copies of itself. This having unlimited copies here. How many copies basically here to complete until reach that the stopping criteria. But it's a small version and calling it own code, right? And set of parameters. These are parameters and set of local variable. If you implement the algorithm, so we have to put the variable. Okay, this is the recursive. Clear?
Clear.
Okay. So we finish the concept of recursive, in particular called recursive method or recursive algorithm. Based on 3 examples, I think from that example, from those examples, I think you can understand clearly what is a recursive algorithm. Okay, now we go to plan for analysis of recursive algorithm. The first, decide on parameter indicating an input size, which is the n. Identify the algorithm basic operation. What is the basic operation? As we discussed last week, what is the basic operation? Still remember?
Summation.
In general, what is the basic operation? Most operation that contribute to the times. Okay, we denote as f of m, right? In asymptotic English, these are general function. F is function from mathematics, and we want to observe the n here when n increases. What is the pattern, the behavior of n when n get large until infinity here? That is the observation from the asymptotic analysis. And sometimes we do not as a t here indicate that running time. Want to observe that the behavior of n when n get infinity here. What is the pattern here? Sometimes we do a C of n. This C basically the basic operation. That is actually the comparison. Let's say involve the searching. Searching we need to compare search key for each item inside the array. In the 0, 1 until the n. That is the comparison. So we do as C. Where this C basically indicate the basic operation, the comparison. So the basic expression can be comparison, can be addition, can be multiplication, so on and so forth. That is basic operation. Okay, clear?
Clear.
Okay. Identify the basic operation, algorithm basic operation, and next check whether the numbers of time the basic operation is executed may vary on the different input of the same size. If it may, the worst, the average, the best case must be investigated separately. And that is set up a recurrent relation with an appropriate initial condition expressing the number of times the basic option. So we need to set up the recurrent relation. What is recurrent relation? Actually, the mathematical from the mathematical perspective, m minus 1, m minus 2, m minus 3. These are the recurrent. After this, I will explain again. Solve the recurrence or at very least establish its solutions order of rows by backward substitution of another method. Okay. In order to do the analysis for the recursive, number one, we need to identify the basic operation. And after that, we need to set up the recurrence. The recurrent form, we need to translate the repetition into recurrence relation, the form. And after that, we solve based on that recurrent relation by using a method called back substitution method. That is the difference between the non-recursive. Non-recursive, we don't use the back substitution method. And for the recursive, we need to use the back substitution method in order to do the analysis for recursive algorithm. Okay. Now the question as raised just now, recurrent relation. What is a recurrent relation here? Okay, many arithmetic functions can be expressed as recurrent relation. Recurrent relation means there is a repetition and relation from this term to another term derived. So m minus 1, m minus 2, m minus 3 until m minus n equal to whatever. You stop the stopping point at 0, you will stop at 0. If 1, you stop at 1, depending on the problem. Okay, that is the recurrence process. Okay, example, n squared, n to power of 2 can be expressed as recurrent relation like this. An equal to an minus 1 plus 2 times n minus 2. This is a recurrent. So this minus 1 is a recurrence. Where ai means the stopping here 2. When a1 n equal to 1, return 1. When n equal to 0, return 0. For this actually we have two base criteria as well. Okay, so we have the function here from the mathematics perspective. We have n minus 1 plus 2n minus 1. So how we get this, the formula, like the question just now, we get the formula factorial or summation, because based on the observation, then we can formulate the criteria. And some of the, not some, all the existing problem basically have already this, the formula, right? Similar like this. Okay, let's say we have n. If n here, n squared here, okay, n power 2. Let's say n equal to 4. Basically, become 4 squared. What is the answer? 4 squared?
16.
Right? Okay. Now we trace here. Is it correct, this formula? So, we need to now 4 minus 1 plus 2 times n. What is the n? 4, right? Minus 1. Okay. And we have to reduce it. 4 minus 3, 3 minus 1 plus 2 times 3 minus 1. And again, smaller version, 3 minus 1 to 2 minus 1 plus 2 times 2 minus 1 and 1. What is the stopping criteria? 1 or 0? 2 minus 1, 1. 1 minus 1 plus 2, 1 minus 1. And this stop. Because the 0 stop, right? The stopping. So can we trace the answer for this? Okay. 1 minus 1, 0. The 0, if n equal to 0, return n equal to 0. Return 0, right? It's given already. Return 0. Okay, 0 plus 2 times 1.
2.
2. So 2. Okay. Okay. 0 plus 2. 2 minus 1.
1.
1. This is the answer if 0, right? If 0. Okay. Here if 1, 2 minus 1. Here is 1 because this written 1. 2 times 2, 4. And 1 plus 4.
5.
5 minus 1.
4.
4. Correct? And this will return 4. 2 times 3, 6, right? 4 plus 6,
10.
10 minus 1,
9.
9. Okay, here we have the 9. 2 times 4, 8. 9 plus 8, 17, 16. Correct? Finally, we got the answer, right? 16. Because 4 squared is 16. So here, if 1 here, if 1 squared, 1, 2 squared, 4, 3 squared, 9, 4 squared, 16. Can you see that the pattern here? This is how basically the recurrence. Understand?
Yes.
Any question? So 1 squared, 1, 2 squared, 4, 3 squared, 9, 4 squared, 16. If 5 squared, 35, right? So we can put if this n equal to 5 squared, 35, and we can trace similar like this, the same thing. This is the formula. That's why we can formulate here. The formula is given already. Then we can trace. Automatically, we can prove that this is actually the answer, the same answer. And this is called the recurrence. What is the recurrence here? 4 minus 1, 3 minus 1, n minus 1. This is actually n minus 1, and this is n minus 2, n minus 3, n minus 4, and so on and so forth. This the form the recurrent. But in the formula, we have only n minus 1. N minus 1, finally n minus 1, the remaining n, 4 minus 1, 3 minus 1, 2 minus 1, 1 minus 1 until 0. 0 will stop because that is the base criteria. Okay? So if a recurrent relation is an equation that recursively defines a sequence or multidimensional array of values once one or more initial terms are given, each further term of the sequence or array is defined as a function of the preceding terms. Okay? This is the same thing as I explained just now. The Fibonacci. Look at this. If Fibonacci is 0, n equals 0, return 0. If n equals 1, return 1. If 2, n equals 2, f1 plus f0, right? If 3, f2 plus f1. This is a recursive. f4, 3 plus 2. f5, 5 plus 3. Fibonacci 4 plus 5, 3. This is called the Fibonacci, recurrence relation. Clear? Clear? Okay. Now we move on to this method for solving recurrent relation. This is important. After we understand the background of recurrent relation, the background of recursive technique, recursive method, recursive algorithm, now we're going to solve the problem by using the recurrent relation, especially for the analysis for recursive algorithm. Okay. No universal method exists that would enable us to solve every recurrent relation. This is the statement, right? There are several techniques, however, some more powerful than others that can solve a variety of recurrence. The first is called forward substitution method. The second called backward substitution. So I will introduce both, but our main concern later after this is backward substitution. So we use this backward in order to solve the recurrent relation or the analysis, to do the analysis for the recursive. We don't use forward, but as a part of this substitution method, I will introduce also the forward. What is the forward and what is the difference with the backward? Okay. Okay. First, method of forward substitution. Starting with the initial terms of the sequence given by the initial conditions, we can use the recurrent equation. Recurrent relation is a recurrent equation to generate the few first term of its solution in the hope of seeing a pattern that can be expressed by a closed-end formula. For example, here we have considered recurrent here. Okay, this is a recurrent. So I think you know the recurrent is in the form of we need to minus 1. Whatever, m minus 1, k minus 1, it depends. We can use either the variables. So let's say we have the x here. This x is a function, right? Function. X is a function. So xn means the functions here. And here 2 times x n minus 1 plus 1. For n greater than 1. Because that if n equal to 1, return 1. It's given already. N equal to 1. So we need to do that return until the n equal to 1. And automatically we return 1, the answer. Because we have the answer already. What is a 1? Let's say this is a function. Okay. So we need to substitute. Let's say if n equal to 2. N equal to 2. So we have this x2 here. We have, okay, 2 minus 1 plus 1. What is the answer? 2 minus 1? 1. So 1 is given already, right? Return 1. 2 times 1, 2 plus 2. What is the answer? 3, right? Okay. If n equal to 3, so we need to substitute. And x equal to 3 minus 1 plus 1. What is the answer?
7.
Because 3 3 minus 1, 2. 2 we return 3, right?
3,
2 times 3, 6,
6,
7. And again, if 4, so 2x 4 minus 1 here plus 1. What is the answer?
15.
15. Right? So we got the answer here. If n equal to 1, the answer will be 1. So if n equal to 2, the answer will be 3. If n equal to 3, the answer will be 7. If n equal to 4, so will be 15. This is the actually forward substitution method. So become increase the values, right? Even though here we have the recurrent here decrease, but the answer for this is actually based on the forward substitution. Okay. Okay, this is the answer basically. But here we can conclude it is not difficult to notice that this number are one less than constitutes power of 2. So we may write the formula like this. X of n equal to 2 power of n minus 1. Is it correct? Let's try. If here n equal to 4, mean 2 power of 4 minus 1. What is the answer?
50.
50. Correct. If 2 power of 3 minus 1, what is the answer? 7. This is actually how we can conclude that formula. The simplified version of this is the forward substitution. So we can prove that the hypothesis that this formula yield the generic term of the solution to B.5 to B.6 either by direct substitution of the formula into B5 and B.6 or by mathematical induction. This is how we can use that induction. Okay, this just to introduce you forward substitution. I'm not going to explain in detail because we're not going to use this for the analysis. Actually, we use the next method called backward substitution method. Clear? Boleh?
yeah,
So, yang ini hanya untuk introduction. We have backward and we have forward. But our main concern is backward substitution method, where we can use it for our analysis later on for the recursive algorithm. Okay. Now we go to the method of backward substitution. Okay, this method of solving recurrent relation work exactly as its name implies, using the recurrent relation. And I hope that you know what is a recurrent relation. As I mentioned, I think many times, what is a recurrent relation? In question, we express x n minus 1. So n minus 1 or m minus 2, that is actually the recurrent relation. Recur, right? M minus 1, M minus 2, M minus 3, M minus 4 until M minus n. And you stop. And substitute the result into the original equation to get x of n as a function of x of n minus 2. That is the idea. We need to substitute the method n minus 1. So we increase n minus 1, n minus 2, n minus 3, n minus 4 until n minus n. If n minus 1 n stopping is 0 and become 0. If n minus n equal to 1, so you need to stop n minus k equal to 1. Something like that. Okay, that is the idea. Clear? Clear?
Yeah.
yeah,
So we have this, let's say the example, we have the function x of n equal to x of n minus 1. Now this is a recurrent, right? Plus n. Now we need to substitute the n here. That's called the back substitution method. And the stopping here, when we write here until x of 0, mean when the n equals 0, you stop, return 0. We return the value 0. Okay, that is the idea. So we need to recur here, the recursive here until stop here, from here. That's the recurrent. Okay. Okay, look at this. As an example, let us apply the method of backward substitution to recurrent B.1 and B.2 just now. That's here, B.1 and B.2. These are B.1 and these are B.2. Okay, here. And Thus, we have recurrence x of n equal to x of n minus 1 plus n. Replacing n by n minus 1 in the equation yield x n minus 1. Because we have the n, replace the n by x of n minus 1 plus n here. Okay. And finally, we can obtain like this. Okay. I think I erase this first. So here, we may write like this. We have now x of n. So we replace n here. So become minus 1 here. So x. We replace it here. Substitute here. Become n minus 1, right? N minus 1, minus 1. N minus 1. This replace the n minus 1. This, and we have the original n minus 1. So become n minus 2. Correct?
Yes.
And plus n here, we need to replace n minus 1. So become n minus 1 and the original n here. So I rewrite here, become x n equal to x n minus 2 plus n minus 1 plus n. Okay, these are recurrence. If we increase again, n minus 1 again, so this become x of n, this recurrent form, x n minus 1 here. So jadi n minus 3 and here n minus 1 plus n minus 2, right? Plus n minus 1, n minus 1 plus n. This is the recurrence. Understand or not?
Yes.
If we increase again, so this become x of n minus 4 plus n minus 3 plus n minus 2 plus n minus 1 plus n. This is a recurrence and solved by back substitution method. So this is a back substitution. N minus 1, n minus 3, n minus 2 until n minus until the n plus n. Okay? Clear? And finally, comparing the three formula of x of n, we can see pattern arising after I such as substitute. So the stopping criteria just now is, what is the stopping criteria? If n equal to 0, return 0. Okay, how we do stop this? This stop n minus what? 0. Okay, let's say this 4, right? You take a very simple 4. Here, n equal to 4. N equal to 4 here. N minus 4, 0. Then we stop, right? This function. And here, what is the value here? N minus 3, 4 minus 3,
1,
4 minus 2,
2,
2. 4 minus 1, 3.
3.
Until n. Can you see the pattern? 1, 2, 3, 4 until the n?
Yes.
Can you see the pattern? So this similar, if you look at the slide, it become here x n minus I plus n minus I plus 1, right? Plus n minus I plus 2, so on and so forth. N equal to 0, 1, 2, 3 until the n. So this is actually the recurrence. And we use the back substitution method in order to get this recurrence, and finally we get this pattern. When we get the pattern, finally we can map to formula number what? This equal to n times m plus 1 over 2. Formula number what? Still remember previously? Formula number apa? Nombor 2 kan?
Dua.
So, this basically become n correct. Is it correct? n squared. This is how we can conclude for the recurrent. We do the analysis and finally we can conclude. You get the pattern like this, then we can conclude as big O of n squared. Okay, clear? Clear? The back substitution method. Ada soalan? Mana formula minggu lepas formula ni? This formula number 2. I equal to 1 until n, I. So you increase 1 plus 2 plus 3 until the n. And finally, we can get this n times m plus 1 over 2 and half n squared. So we can conclude this, where we got this pattern, basically we can conclude as n squared. Clear? Clear?
Clear.
Okay. So in conclusion, in order to do analysis for recursive, number 1, we need to set up the recurrence. These are recurrent. These are recurrent. Here, these are recurrent. And after we set up the recurrent, we have to apply the back substitution method like this. And when we apply the back substitution method, we can see that pattern like this. If it wasn't pattern like this, then maybe we may map to certain summation formula, or maybe log like we did for the non-recursive algorithm. And finally, we can conclude what is the big O for that particular recurrence or recursive algorithm. Clear?
Yeah.
Okay. So we continue the next slide, which is the example of recursive. Okay. Like this. Let's say example. These are factorial what we discussed before this, the previous slide in the introduction. Okay. We have the factorial integer n, integer result. If n equal to 0, return 1. Result equal to 1. Else return result n times factorial m minus 1. So the first step, you need to establish the recurrence form, the recurrence. So where is the recurrence here? From this. Okay. What is the recurrence? So we can denote as T. T is the running time, right? We may use the F. F is general functions for the n. So now we go specific is running time. T of n equal to, okay, T of n minus 1. And this actually plus 1. Plus 1 is 1 by 1. We use 1 by 1. Just now we use just now, the example just now we use the x, right? X of n equal to x of n minus 1 plus n. The recurrence. But now n minus 1 plus 1. So just now we use the x. This is a general variable function here. But now we go specific for the t. T is a running time. Want to estimate the running time for this. So the recurrence is t of n equal t of n minus 1 plus 1. Okay. These are recurrence. This is called recurrence relation. The population. You got ready. Okay. Now we need to derive from this. And based on the back substitution, how are we going to substitute it? So we have this t of n minus 1, right? Here we need to substitute here. So this become t and what?
N minus 2.
2 plus 1 plus 1. Is it correct? This
Yes.
one is the original, this one is another. Okay, then we need to substitute n minus 1 again for this. So n minus 3 plus 1 plus 1 plus 1. Is it correct? Clear so far?
Yes.
Yes. Time. There's no n because the recurrence is 1. Just now, this previous example, n, but now it's 1. Because for this factorial, is actually is a time 1. Every time it's 1 only. It's a different case. No n, 1. The recurrence is t of n minus 1 plus 1, not n. Different with the case study, the example we discussed just now. These are based on factorial. Clear? So basically, it will reduce when call this only one iteration, iteration for each. So when it is n, this basically it will repeat one by one. That's why plus 1. Okay, clear? Maybe you get used with previous and just example basically, just example. There's no algorithms we can use this, but normally when we use factorial, basically when we use like this, just now factorial n time factorial n minus 1, correct? So this we reduce, let's say 4. 4 become this 4 time factorial 3, right? And 3 time factorial 2. This is actually 1 by 1. That's why in the recurrent, recurrent is TMO plus 1. So every time it will reduce m minus 1, it reduced by 1, 1, 1. So the process basically is 1 by 1, plus 1, plus 1, plus 1. The repetition. Sometimes maybe repetition based on n time. This is only one time. For this factorial. Clear? Clear so far? Okay. That's why we need to set up, and finally we got this. This is a recurrent. T of n, this is form a recurrence plus 1 means every time repetition is 1. 1. For each repetition 1. For each repetition 1. Clear? Okay, here next, if n, again n minus 1 become 4. Plus 1, plus 1, plus 1, plus 1. Okay, so how we stop? The stopping criteria is if t equal to n equal to 0, return 0. n equal to 0, return 0. So mean n will return 0. Return 0 is automatically it will produce that the result 1. We don't calculate it. Okay. So now how to stop this? Until here. 0, then return 0. Okay. How to stop at 0? N minus what? 0.
4.
So you use n until here, whatever. Maybe you put the k here. So when n minus k equal to 0, mean n equal to k, right? Correct. So we can see that observe if 2 here we have 2. If 3 we have 3. If 4 we have 4. If until k here mean here is k. Until k. Correct? So k equal to n. Because n minus k equal to 0, right? So k equal to n equal to k. So what we can conclude here? In terms of the big O? Yes.
ON.
ON, correct. Because when we observe the pattern here, when this recurrence relation until reduce until stopping here 0, so the pattern when these 2, we have 1 plus 1. The 3, 1 plus 3 also. And 4, 4, and this actually 1 to 3 until the k, this is actually similar to the k. And finally the k actually equal to n. and we can conclude that this equivalent is O(n). O(n). Clear?
Clear.
Ada soalan? Tak ada? Tak ada eh?
Tak ada.
Okay, no. Now, we move to example 2. Look at, tentu power, integer x and integer n. So, when n equals 0, return 1. So, as result, okay, based on this, based on the formula, in the algorithm, we have x times power x and minus 1. But we need to accept this only. So, for the second step, to set up the recurrent relation, become t of n equal t n minus 1 plus what? Is it plus n? So, plus 1. This is similar to the factorial just now. Because every time it will, for every iteration, basically is only one iteration. Next one iteration. Not n iteration, not n time. One time. Clear? And T0, start at T0 equal to 0. So basically, when we do the analysis, the same thing, right? So this becomes T of n 2 plus 1 plus 1. And finally, n3 plus 1 plus 1 plus 1 until stop. And m minus k 0, then this become O n. The same thing. Clear?
Clear.
Clear, sir.
Okay. Next. Example number 3. These are maybe a bit tricky. Okay, look at example number 3 here. 3 here. Okay, we have the called binary n. Okay, and finally, if n equal to 1, return 1. Else, return this recursive binary called itself, right? The same thing here, but here is okay, n over 2, take the floor, okay, plus 1. So first we need to set up the recurrence. So how to set up the recurrence? So we have a t of n equal to t of n over 2 plus 1. The stopping given is here t of when n equal to 1, 0. Return 0. Okay. It depends on the problem, but here is when it stop 1, so there's no iteration. 0 iteration. Just return the value. So t of 1 here is n equal to 1. So 1i equal to 1, n equal to 1, return 1. So the return 1 is the value, but the iteration stop. Clear? There's no iteration after that. When n equal to 1, that's why you put the 0. Because remember, we need to calculate the how many repetition done for that recursive. Because that would contribute to the basic operation, whether it is in a linear n or maybe n squared and so on and so forth. Okay, that's why we need to do that. Okay, and okay, now we have this recurrent, right? But this recurrent Is this in the form of recurrent relation? Here, n over 2. What is the form of recurrent relation? We must have whether n minus 1, n minus 2, right? So now it's not in the form of n recurrence relations. We cannot apply the back substitution in this form. So how we to change this to convert into the recurrent relation? So we need to, let's say, based on the formula here, let's say we have n equal to 16. Look at this. If n equal to 16, 16 by 2 equal to what? 8. 8 by 2 divided by 2, 4,
4.
and finally
2.
2. Right? 2, 1. Stop. So what is the pattern here? What is the pattern here? 2
Vector.
power of 0, 2 power of 2, 2 power of 2 power 1, 2 power 2, 2 power 3, 2 power 4, right? Until 2 power OK. Correct? This is a pattern for the n. Is it correct? Similarly, what we did for the non-recursive function. This is better. Is it correct?
Yes.
Yes, sir.
And now we can write like this. T 2 power of k over 2 plus 1. But this still not in the form of recurrence ratio because we need if k minus 1, k minus 2, so that we can substitute. So we can change this to 2 power, t 2 power of k minus 1 plus 1. Is it similar to bagaimana equal to 2 of k over 2? Is it similar?
Yes.
Okay. Cuba prove. Let's say just now 2 power of 3 divided by 2. What is the answer? What is the answer? 2 power of 3. 4. Okay. Now, what is the k? 3, right? So now, if we substitute this, 3 minus 1, 2. 2 of 2, 4. Correct? Basically the same, right?
Yeah.
Okay, why do we need this, the form? Because we need 2k minus 1 is in the form of recurrence. We need this. So we need to change to this form. 2 power of k minus 1. So that we can do the rest of the recurrence back substitution method. Okay. Okay, need t. Okay, now we can t 2 power of k minus 1 plus 1. Correct? And that we need to substitute. K minus 1 become 2 power of k minus 2 plus 1 plus 1. And again, 2 power of k minus 3 plus how many 1? 1 plus 1 plus 1. So you can see how to stop. Stop at, what is the stopping? T1, right? T1 go to 0. So how to start 1? 2 power of what? Return 1? 0, right? Correct? 2 power 0, right?
Yes.
Fine. Okay, now we're going to stop here. And 2 power 0, return 1, return 0. And so we can see, we can observe that if k minus 1, 1, k minus 2, 2 until the whatever k here, maybe k minus k, 0. Then here is actually k, right? Okay. This k, what is the pattern for the k? Is it n? K equal to n. Like what we got just now. K to n.
Yes.
Yes. No. Not equal to n. Because just now, we assume that the n here, the n is 2 power of k. Correct?
Log n.
The answer will be log n, because the k here is not equal to n. Because the k here is actually based on this 2 power k, and 2 power k is equal to n. Correct? Is it correct? So just now we have n equal to power of k. The pattern that observed now is until k. Here k is here, not equal to n. So the n is equal to 2 power of k. So we need to find what is actually the pattern increase 1, 0, 1, 2 until the k here is, we assume that is a log. Then we put the log to 2 power of k. Here is log n. And now we can got this k times log 2 base 2, and this are log n. And finally we can simplify here. This become the pattern that we observe now is k here is equal to log n. Is it correct?
Yeah.
Tadi n minus 1. n minus 1, minus 1, minus 2, minus 3, until minus whatever k. And here is a k, but k equal to n. But now, because 2 power of k, not the n equal to power of k, then we can have a k minus 1, k minus 1, 2, k minus k, 0, and k now is not equal to n. K is actually 2 power of k equal to n. Yes, but not n. Clear? Clear or not?
Clear.
Okay, any question?
So log tu base 2 ke?
Log ni biasa base 2 lah. Kalau kita sainkan dulu yang introduction tu, normally use a base 2. So macam ni base 2 kita boleh simplify terus. Because log 2 here, log 2 base 2 is 1 lah kan? 1. So k times 1 k. So now the pattern based on the k increase k 2 power k, k 1, 2, 3 until whatever is actually log n, not n. Boleh?
Boleh
So
Doktor.
log n tu base 2 lah.
Base 2. Base doesn't matter sebenarnya.
Oh.
Base is okay. Base 2, base 10 is okay. Yang penting kita nak n saja. Log n tu. Natural log pun is okay. Macam yang bagi example yang previously, yang apa tu, log tu, natural log, example non-recursive number 2. N log n, kan? Kita nak that log tu sebab kita estimate. So the pattern is actually log based on log. Whether log 2, log 10, log doesn't matter. But normally we use the binary log 2 because computer science use a binary based on the binary representation, binary code. Okay, clear?
Okay.
Ada soalan lain? Ada soalan lain? Tak ada? Understand which one? The whole thing. Which part you don't understand? Huh? 2 power k over 2 ni. Kan? Sebab tadi n over 2, right? So, for simplicity, we can put the n equal to 8 for example, or 16. So, if 16 divided by 2 equal to 8, right? And 8 divided by 2, 4. 4 divided by 2, 2. 2 divided by 2, 1. This is the pattern. So, this pattern basically similarly to here, 2 power of k. Because pattern here, look at this. If 2 to 1, okay, 1, 2 power of 1, 2 power of 2, 2 power of 3, 2 power of 4. Correct? 2 power 0, 1. This is the pattern. 2 power 1, 2 power 1, 2, 2 power 2, 4, 2 power, this is n, this n. Don't forget this n. 2 power 2, 4, this n. So this is actually n for this case. And this 2 power 3, n. 8, this power 16, this n. So the pattern here is 2 power of 1, 2, 3, and 3, whatever 2 power of what here. Then put the k lah, whatever lah. This is the pattern of n just now. So this similar to n here, n over 2, we have t of n over 2 equal to t of n 2 power of k here over 2. Clear? Now, this, even we put in this form 2 power k, but this is still not in the form of recurrence relation. Because recurrence, we see, must be, we have a -1. Then we can start the recurrent and use that, the back substitution method. So how we translate this from the, okay, just now we have t n over 2, then equal to t 2 power k over 2, right? Then we change to t power 2 k minus 1 here, because we need this form, which is the recurrent relation. Okay, macam mana boleh dapat 2 power k minus 1 ni? Dah tak ada lah. Kalau ada masa ni sebab, kita tengok. Kalau tadi kita ambil 2 power k berapa? 3 kan? 2 kali 3 berapa? 8. Bagi 2? 4. So sekarang kita ambil k tadi berapa? 3 kan? Okay. 2 kuasa 3 tolak 1. 3 tolak 1? 2. So sekarang jadi 2 kuasa 2. 2 kuasa 2 adalah? 4. Kan proof sama? Sama lah. 2 kuasa k bagi 2 sama dengan 2 kuasa k power kuasa k minus 1 sebenarnya. Dalam matematik. Kenapa kita nak macam ni? Sebab kita nak this k minus 1 ni. Baru kita boleh guna back substitution dekat recurrent relation. Boleh faham? Clear tak? Jadi kita nak tukar pada ni, baru boleh dapat recurrence. Bila dapat recurrence tu baru kita boleh k minus 1, k minus 2, k minus 3, k minus 4 until k minus what equal to kosong. Equal to 1. 2 kuasa kosong 1. Then dia stop. Boleh?
Boleh.
Okay. Clear Jangan di-confuse pula. Itu kan sama masa yang dekat non-recursive kan ada kan? Tapi sini recurrence kita nak itu supaya kita tukar jadi recurrence, itu ada k minus 1. Yang dekat recursive kita tak perlu, kita 2 power k je. Kalau kita nak tengok pattern tu. Okay, next. Okay. Ada kala ni kalau contoh soalan ada masa bagi agenda you have to set up the recurrent. Ada masa bagi recurrent terus, dan you terus apply the back substitution method. Faham? Boleh faham? Contoh
Boleh.
Contoh ni plus 5. Benarnya in the real algorithm tak ada pun plus 5, mana satu je. Tapi this is for the case untuk analisis. Plus 5 ni sama plus 1 je. Dia constant tau. Constant ni tak ada apa. So kalau ini kita buat macam mana? Kita boleh cepat. Kalau ini dapat apa ni? N minus 1. Oh sorry. Ni N sama T of N minus 1 plus 5. So jadi Tn minus 2 plus 5 plus 5. This is constant. 1, 5, 10 basically the same. And n minus 3 plus 5 plus 5 plus 5. Okay. What is the stopping is T1 equal to 0. How to stop is, can I stop? equal to 1, T, and minus K minus K equal to 1. Alright? N minus K, if N 4, K must be 3, right? 1, stop 1. So plus, here is how many here? If 1, 5, 1, 5, 2, 2, 5, 3, 3, 5. So jadi here is 5K, right? Is it correct?
Yes.
5K. So what is the K here?
N minus 1.
K is equal to N minus 1. Is it correct?
Yes.
Betul kan? But if N minus K equal to 1, this is mathematics, N minus K is 1, then K, if K equal to N minus 1, correct?
Yes.
Okay, so here we stop, then we have 5N minus 1 equal to 5N minus 5. So we can conclude element of what?
N.
O N. Correct. Simple. Boleh faham? Boleh? Boleh? Ada soalan? Satu lagi. Belum habis. Ada soalan ni? Ada soalan? Yang ni? Clear?
Yes.
Yeah.
Okay. Tak ada. Kita go to the second here. Okay, we have T of N, the recurrent form. These are actually what we example just now. Just now was X of N, but now N specific we have N. N times. Just now one time. So N greater than 1 is stopping is T 0, mean N equal to 0, return 0. Okay. Okay, here, this becomes T of N minus 2 plus, substitute here, N minus 1. Substitute here, N minus 1, right? M minus 1 plus N. Okay, clear? In until this point, clear?
Clear.
Okay, next we
Yeah.
use this. N minus 3, this becomes plus N minus 2 plus N minus 1 plus N. Okay, again, one more round. N minus 4 plus N minus 3 plus N minus 2 plus N minus 1 plus N. Okay, now we're going to stop 0. So how to stop 0? N minus what is 0? N minus N, right?
Yes.
Okay, 0. Let's say N is a 4. 4 minus 4, 0. 4 minus 3, 1. 4 minus 2, 3. So this pattern becomes plus 1, plus 2, plus 3 until N. The pattern for this. Is it correct? Is it correct? Macam mana yang tadi?
Yes.
Betul?
Betul.
Okay. So when we have this pattern, basically we may look at the summation formula. If this pattern basically the same pattern with the summation formula. This summation formula number? No, number 1 plus 1 plus 1. Number? Look at these patterns. Okay. Okay. Here. Number what?
Number 2.
Okay, number 2, then we can conclude. So this becomes basically N times N plus 1 over 2, right?
Yes.
O equal to half n squared. Element of BO of n squared. So we can conclude this. Or simply m squared for this. This is the upper bound. Still remember the upper bound? The BO is upper bound. The maximum input over the maximums over the input and input input size. So now for this algorithm, for this recursion, the BO is O n squared. Clear?
Yeah.
Okay, last one.
Sekejap, saya tak faham.
Faham kat mana tu?
Macam mana daripada semua tu dapat N tambah 1/2?
Ni. Oh, ini panjang cerita. Ini pemuda dah bagi dah. Sebenarnya kalau you nak.
Tak, tapi macam mana daripada atas tu
N
dapat
satu.
bawah?
Mana? Pada atas mana? Ini. Okey, saya pandang balik lah.
Ikut pattern.
Ke pattern. Kat mana tak faham? Ini faham? Ni. Kan kita nak substitute n-1. Jadi sekarang ni kena substitute kat sini. n-1 untuk di sini. n-1 dekat atas ni. n-1 minus 2 kan? Jadi n-2. Lepas tu yang sini kena substitute n-1. Jadi n-1. Yang n the original. Kita kena substitute the whole thing here. So finally kita dapat n-1 equal to n-2 plus n-1 plus n. Kat sini faham?
Okey.
Okey. Kemudian kita kena recurrence lagi. n-1 lagi. n-1 untuk ni, n-1 minus 2 jadi n minus
3,
3. Yang ni n-1 campur 1 lagi, n-2.
2.
Kemudian ini n saja tadi, n-1 jadi n-1, n plus n the original. So kita dapat ini. Boleh faham?
Faham.
Okey, yang ni samalah. So jadi n-4, n-3, n-2, n-1 nanti n. Boleh faham?
Okey.
Okay, now kita nak stop because that the base comes yang progressive kan, mesti ada stopping. Ni dia dah repeat. Repeat. Nak stop. Stopping is T of
Equal to 0.
0 equal to 0. Mean equal to 0, there's no repetition. Ni semua repetition. Okay, now macam nak stop 0 ni? Kalau kita ambil sampai 4, bermakna n minus apa 0?
N.
Of course n kan? Jadi kalau n minus 0, yang ni kan decrease by 1. Kalau ambil 4, 4 mana 4 kosong. Sini 4 tolak 3, 1. 4 tolak 2, 2. 4 tolak 1, 3. Campur dengan n tadi 4. Jadi 1 campur 2, campur 3, campur 4. Nanti dah n lah. Boleh faham? So pattern ni sama dengan pattern yang tadi dekat apa ni n I here kan. 1 sama dengan 1 plus 2 until the n. Summation formula number
2.
number 2. Ni mana tadi? This pattern. Kan? I equal to 1 until n, I. So I plus 2. Jadi equal to n time n plus 1 over 2 or half equal to half n squared. This actually, so we can conclude as O n squared. The pattern here. Boleh? Boleh faham?
Okey.
Boleh ke tak?
So 1/2 tu abaikanlah. Dia jadi O terus lah.
Kan dulu kita dah define constant itu boleh omit kan? It
Betul.
won't affect the real time. Yang kita consider is the n. Kan dulu kita buat tu ada 3 plus 3n kan? Ini kan constant kan? So kita boleh omit, ignore, dan kita boleh convert as ON. Sebab constant always constant. Ni half always half. But our constant is only the n input size, the variable here. So we can put as n squared. Ataupun kalau yang paling tepat kita tulis macam ni jawapan dia. Half n squared element of O n squared. This is the best answer. Or only you can put n squared also. Pun okey, boleh. Ini paling jawapan paling tepat. Boleh?
Okay, thank you, sir.
Okey. Ada soalan lain? Siapa yang rasa masih confused, tanya kawan-kawan yang boleh faham ya. Sebab online susah sikit nak ni. Okey, last question. Last question ni benda yang sama tadi kan? Betul tak? Yang sama tadi kan? T of n equal to T of n over 2 plus 1. So ini kena tukar jadi T of 2 power k over 2 plus 1. Okay, kena tukar lagi jadi T of 2k minus 1 plus 1. Because we need to form this k minus 1. Okay. Then baru from there, baru kita boleh buat back solution tadi. Okay, k minus 1, k minus 2 plus 1 plus 1. Then again, k minus 3 plus 1 plus 1 plus 1. So this stopping is 1, right? In order to stop is 2 power of 0.
0.
Become 1. So here is similarly like 1, 1, 2, 2 until k minus k. So here is k, right? K. But the issue now whether is k is equal to n. Adakah sama k equal to n? The pattern is 2 power of 1, 2 power 2 until 2 power of k. K ni adakah sama dengan n?
Tak.
No.
No.
2 power k equal to n, right? 2 power k equal to n. Baru betul kan? Because we take that just now 2 power k over 2, which is this n. So when n, so if not n must be log n, slightly less than n. So we put assume that this log 2 power of k, 2 power of k base 2 equal to log n. Then we need the k only. So k times log 2 base 2 equal to log n. So we can simplify here. So k equal to log n. So I just repeat the same thing. Clear?
Yeah.
Okay. We have done basically all. Ada soalan? Clear tak?
Last.
Those yang
Yeah.
masih confused, please ask your friend yang mana dah faham tu, please share. Sebab maybe sometimes a bit confusing in terms of the recurrent relations. Okay. Any other question before we stop? Ada soalan? Ada soalan? Tak ada?
Tak ada, sir.
Okay. Kalau tak ada, can we stop here? And see you next week.
Yes, tak.
Boleh.
Boleh?
Sir, saya nak tanya pasal assignment boleh?
Boleh?
Saya share screen ke?
Dia tanya jawapan ke dia tanya ni? Jawapan tak boleh lah.
Tapi saya tak tahu macam mana buat.
Yang mana tu?
Sekejap.
Kalau tanya jawapan nanti saya pula jawab assignment, saya hantar, saya dapat markah lah. Dah share belum?
Macam algoritma 1 ni kan, bila dia nak stop? Dia cakap dia lebih daripada 2.
Bila nak stop, bila dia divide, dia akan stop lah.
Oh, dia akan divide sampai kecil
Mestilah, divide tu dia akan kecilkan macam tadi lah. 8 divide 2 ni akan stop bila dia less than 2. Then dia stop. Jadi masa stop tu dia tengok lah dia punya looping tu berapa kali. Pattern dia apa? Pattern dia 1 by 1 ke 1 plus 1 plus 1 atau maybe pattern dia log. Lagi?
Sir, yang algoritma 1 tu, yang atas sekali tadi, Cak, tolong. N memang N lebih besar sama dengan 2 bukan N sama dengan 2.
N lebih besar atau sama lah. Sebab kalau 2 bahagi 2, 1 kan? Dia start kalau 2 lah. Mana boleh lebih besar? Lebih besar atau sama? 2 dikira lah. 2 bahagi 2, 1. Dan 1 dia stop lah.
Jadi tu kira macam limit bawah dia lah. Nombor 2 tu.
Kan? Ini kan algoritma.
Kalau
Bila you nak through, kan programming part this. Apa tadi? N. Apa tadi saya tak nampak? N greater than 2 right? Y N greater than 1. Kemudian
N equal
N equal to N over 2. Okay. Cuba tulis. Katakan N tu mesti besar pada 2. Apa yang besar pada 2? Besar atau sama? 2 lah. Katakan ambil 8. 8 besar pada 1. Confirm kan? True. True buat ni. So 8 bahagi 2. Jadi assignkan N. Jadi 4. Jadi N sekarang 4. 4 bahagi 2. 2. Assign 2. 2 lebih besar 1. True lagi. So 2 bahagi 2. 1. Dan 1 dah pause. Stop lah. Kan?
Yep.
Stop. Then observe the pattern lah. Apa pattern dia? Boleh?
boleh, sir.
Ada yang lain. Saya tak nak bagi jawapan lah. Sebab ni assignment. Saya bagi head je. Nanti kan saya pula menjawab soalan.
So ni macam mana nak buat, sir?
Macam mana nak buat? Tu kan ada 3 loop tu. 4I, 4J, 4K kan? Tulis lah. Pattern dia macam mana? Itu kan 4I. Cuba baca kat saya tu. Baca kat saya 4 apa tu?
4i equal to 0 to n tolak 1.
Okay, 4I equal to 0. Lepas tu
N tolak 1.
N tolak 1 until kan? 2 N minus 1. Do kan? This code basically, this to the code programming adalah sama dengan ini. For I equal to 0, I less than N minus 1, I plus plus. Macam ni kita nak tahu dia plus ni, dia increase by 1 sebab kita tengok algorithm tu kan. Itu multiplication, dia akan compare, calculate, multiply A dengan B tu. 1, 1, 1. Dia pergi 1, 1. I plus plus. Inilah. So yang ini kita nampak lah sebenarnya ini kalau you buat summation adalah N minus 1. Yang ini I equal to 0 increase by 1. So this pattern 1 plus 1 until the N. Dia nampak dah. Dah nak menjawab soalan tu? Boleh? Clear? Ada lagi yang lain?
Ni apa sir yang CI, J ni?
Oh, CI, J kan kat atas lagi. Itu kan metrik. Metrik tahu tak metrik? Metrik. Kan CIG ni metrik kan? Metrik matricia kan? IJ kan? Ni kali ni kan? Kita tengok metrik multiplication.
Okay. Tujuh kot.
Ada lain? Tak ada? Ada lagi? Group C nanti saya postkan apa ni assignment yang 3 untuk analisis. Nanti esok tak ada lab cuti dan terus buat ya. Boleh?
Boleh sir.
Okey. Ada soalan lain? Kalau tak ada, kalau tak ada boleh stop. Siapa ada saya boleh tunggu sampai last yang student yang apa ni? Last student lah. Okay. See you next week.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Sama.
Thank you, Doktor.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.